Derivatives. I love derivatives. I do not mean that in a joking way. Derivatives are really a lot of fun. You do one of them, you're like, okay, it's good. But it's like eating a pack of Oreos. So, you eat your first Oreo, you're like, I'm just going to eat one Oreo. But then you get back and you eat a second one. And before you know, the entire box of Oreos has entered your mouth and is currently digesting in your stomach. Differentiations like that. So we're going to be starting off teaching you with the most Oreo-esque versions of differentiation, which is with the simple methods for differentiation, using your differentiation rules. So the differentiation rules are as follows, and we'll just write them up here. It's pretty straightforward here. We have our first one, which is going to be, what is this? This is going to be your x, whatever you're starting off with. So say if you're looking at this, or f of x, I'm sorry. No, it's just x. I didn't get that. It's y. This always confuses me. So you have your y, and then you have your dy dx over here. Okay? That's really all it is. And then you're looking at, so this is your undifferentiated, whatever y equals, so say y equals x squared. And then this will be your differentiated version, which is 2x. Whoa, where'd that come from, man? We'll show you where that came from. But give you an idea of it. This is the most nifty method to do differentiation by. You can obviously always go back if you're having trouble and you need to figure out how to work it through. I strongly encourage you to go back and take half an hour with your limit of h going towards 0 of your f of x plus h minus function x over h, but this is a little bit easier. This is like, say, eating toffee. You eat one toffee and you chew on it for a while, you work it around, and you gotta play with it with your tongue, you try to get it down, and it takes you a while. It's work, okay? This is like Oreos. You're eating the Oreos, they're gone, man. So, toffee, but it'll give you a bit of a tease for your tongue. But the Oreos, that's where the good stuff's at. I'm a big Oreo man, if you haven't noticed. So, here we go. So, for our first version, it's the most simple, straightforward. It's just in the form ax to the n. What is that? That's 3x to the 4th. 2x cubed, 9x, or just 9x to the 1. Okay, it's that kind of form. Or even, if you're looking at it, you could look at constants, which would just be 4. In this case, 4, and then it's actually x to the 0, because remember guys, all the way back to exponents, x to the 0 equals 1, so that means I could just write this as 4x to the 0. So this little result here is the most important differentiation result. It's going to guide basically all of differentiation, and it applies to situations like these. Okay, so what does that differentiate to? Should have kept this up there. So let's say for 3x to the 4th. What you do is you take a n x to the n minus 1. Whoa. What's going on here? Straightforward, okay? All that happens is your constant up front, your coefficient stays the same, still multiplying it by it. You drop down your exponent right there, drop it down to multiply by in front, and the exponent is subtracted by 1. For example, take a equation where you have slope. Remember all those days back in the good old days where you're like, well man, it's just slope's just that number. When you've got your y equals mx plus b, this is why that's slope. Because b is b times x to the 0. X to the 0, b times x to the 0, yes. So when you have that constant, it ends up getting canceled out. You don't worry about that for slope. And then, you looking at it, you say, okay, because, why would this happen? Because when you're looking at your constant, you say x to the 0, you drop down that exponent down here, so now you have b times 0 times x to the negative 1. 0, that's going to equal 0. And then your m to the x, 1, is going to end up being that 1 drops down, so it's 1m times x to the 0, which is just 1, which will in the end will just equal m. There you go. And that is why your slope on linear equations will always just equal what's multiplied by the x. And all this is it's just upgrading this formula so it can work for larger quadratics. For example, 3x to the 4th. You drop down your 4, so now you have 3 times 4x to the 3 is 4 minus 1, and that just gives you 12x cubed. Pretty straightforward. We'll run through 2 more real quick just so you get the hang of it. Let's do, say, go for a little bit of fun. 3 square root of, we'll just leave the 2 on the outside. 2 cube root of x squared. Okay? So, what does cube root mean? It means 2x to the 2 over 3. This works perfectly fine. You drop down to the 2 over 3, which means it's going to be 4 over 3 x minus 1, which will just be negative 1/3. And you're done. Boom. If you'd like to put it back in the form like where it was previously, you can go and say this is actually going to equal 4 over 3 cube root of x, if you felt like that. You could do that. It's perfectly acceptable form. Because, see, you have your negative exponent, which means it's going to be in the denominator, and your fractional exponent, which means it's going to be a root. There you go. And one more example. Let's say you have a negative exponent, which means 4 over x cubed. Well, it's going to be 4x to the negative third because it was in the denominator. 4x to the negative third, it's just going to be negative 12. Can't write today. Negative 12 is you drop down that negative 3, and then you have your x to minus 1 again, so it's not going to be negative 2, it's going to be negative 4. Because negative 3 minus 1 is going to give you x to the negative 4. If you choose to go back to your original form, you get negative 12 over x to the 4th. As you drop it back down to get rid of that negative. There you go. That's your basic differentiation result. Now, there's a few other results as well, and we'll show you them real quick. You also have your result for e, which is a e to the x, yes. A e to the x, which in this case will simply equal ax e to the x. Why is this? It's because e is the number, which is slope, is its own derivative. Or in other words, for e, the basic e, if you ignore the a, you're going to see bloop, what's wrong? E to the is going to be, if it's, one second. So e is its own derivative. So we're going to show you the basic e first. So e to the x equals e to the x. And that's the definition of e as a number. It's the number for which, for every x, its own slope is going to be itself. Which is kind of cool when you think about it. However, if you add an a there, so if you say a e to the bx, you're going to end up dropping down that b, so you get a b e to the bx. Keeping that up there. So run through a few examples. Let's say the basic for e to the x, well, it's just going to end up being 4 e to the x. Because nothing drops down, nothing really changes, and e is its own slope. However, if you had 2 e to the 5x, then it's going to end up becoming 10 e to the 5x. because the 5 drops down, multiplies by the 2, and you keep this number the same. No matter how many times you differentiate it, that number will always stay the same for e. Straightforward. Next up, what if you have the opposite of e? The opposite of e, what's the opposite of e? ln. So if you take ln of x, what you end up getting is going to be 1 over x. So with ln of x, you get 1 over x. There you go. And it's pretty straightforward. The one thing to keep in mind for the ln of x, and you'll see why this is later, this is the chain rule, but if you have ln of, say, 4x, that 4 isn't going to be the final result, so it's just going to end up still being 1 over x. And I'll come back and show you why that works. However, if you do have 4 ln of x, it's on the outside, it'll do the same thing it would do normally, and you just end up getting 4 over x. Okay? So let me clear this out, make this a little prettier here. So we've got our basic result. We have our e to the x differentiates to be e to the x, our ln of x differentiates to be 1 over x, and we're going to leave it there for right now. There's also 3 trigonometric results, but we're going to come back to those and run through them at the end of the video. We're not going to do them quite yet. Shabu. So leave that up there, keep those in mind. However, what if you have something that's not one of the basics? So let's take, before we do that, let's take a real quick run through and just give you a chance to kind of think about them. Uber long equation, 5 x to the 3 plus 5 over x squared minus 3 square root, we'll make it the 5th root, of x, and plus 4e to the 5x minus ln of 2x plus 4 ln x. Okay, so if you like, I recommend you pause the video, work through this real quick to give you a little bit of practice, and then come back. And you're back. Here we go. So we take this out, 5x to the 3rd, you drop that 3 down, is going to end up equaling, so we'll just arrow over here, is going to be 15x squared, subtract 1 from your exponent. This one is 5 over x squared, but it's really going to be 5x to the negative 2, which just means 5x to the negative 2. 5 times negative 2, you drop that negative 2 down, negative 10. So negative 10x to the negative 3. And then, because you subtract 1 from your exponent. Then we have negative 3x to the 1/5 power, which is all the root means. 3x to the 1/5 power will end up equaling minus 3 over 5, because again you drop it down, x to the negative 4/5. Next up we have 4e to the 5x, drop that 5 down, 20e to the x, plus 20e to the x, 5x, you maintain the 5x. And then ln of 2x is still going to be subtracted. Remember that 2 doesn't have any effect, so it's just going to be 1 over x. And finally you have 4 ln of x, which is going to be plus 4, because it's just multiplied by the regular result, which is 1 over x. Okay, there you go. Now it's time to move on to some more higher level stuff. And this is when you have 2 results. Head back to the table here.